All right, let's do some math.
I'm gonna leave this meeting. That's what I'm
You don't want to.
kidding.
You don't want to do some math?
Nah, it's
All right,
not.
all right, Mrs. Contreras, you need to pick a color. I'm gonna pick a color because we're graphing multiple curves at the same time, and it's in. Are you purple?
Yes, I'm purple.
We're graphing multiple links at the same time. The reason why I said, "Hey, are you purple?" is because everyone. Now I'm sharing my screen. I was crabbed while I wasn't sharing my screen. So you're purple. I'm gonna be. I don't want to be blue because blue and purple are very close. I'm gonna be like a nice pink. That's what I'm gonna be today. Boom. All right, so this is me. I call graphing this one.
Okay.
All right, so we are graphing a system of polar equations. So first video, we got introduced to polar, new coordinate system. Second video, we were introduced to many different curves, functions of theta. So r as a function of theta. You give me a theta, I give you a radius away from the pole.
Mhm.
And what we're going to do today is we are going to graph them at the same time and then find coordinates that satisfy both equations. Now, before we do this, I like that you identified that yours is r equals -3 by putting a crab next to it. Awesome.
Thank you. Before we do this, whoa, you can copy things?
You're better drawing crabs than me, so I'm just taking your crab. I've plagiarized your crab.
All right. I guess it's
Anyways,
okay because it's for educational purposes.
well, don't say that. Plagiarism is not okay, even for educational purposes. It's particularly bad. Anyways,
I demand some royalties, Mr. Kirk.
there you go. Anyways, where was I? You said where I was, and then I proceeded to plagiarize your crap.
So before we get into graphing this, should we think about what we're doing first?
Yeah. So wait, yeah. So I'm gonna go ahead and draw a rectangular coordinate system, Cartesian plane here, and I'm gonna draw two curves. If I said, I don't know, maybe this is like y equals f of x, and this is like, I don't know, y equals g of x. If I said, what is a solution to this system of equations? And you know what? I don't like that I used arbitrary curves. I'm going to use lines just for the sake of simplicity. I give you y equals. You don't like my lines?
Not really.
I guess they do curve a little bit. This is more like, this is like 2x minus 5, and then this other one's like x plus 1, whatever. How would you find a solution to the system of equations y equals 2x minus 5 and y equals x plus 1?
Well, the solution is what makes both of those equations true.
Okay.
And that would be at the intersection of those two lines. So wherever that happens,
boom,
that's their solution.
Which is happening
one
somewhere.
Solution.
Yeah. So we could look at the graph. Like if we had actually well graphed two lines, obviously mine are not. You've already made fun of them. If we can look at the graph to find out when they intersect and we have a solution. How else might I want solve this system of equations?
Well, we can take our two equations and we can set them equal to each other.
2x minus 5, x plus 1.
And then solve from there. So we should get like 6.
Yeah, and then
plug that in, so we get like 7.
6 comma 7. Kind of looks like 6 comma 7.
Sure.
All right, so we have a coordinate 6 comma 7. That is the solution to our system of linear equations.
Mm-hmm.
How else might I do it? Just as like an aside. Can you think of anything else?
Well, you could do like the elimination method where you like multiply. You can multiply like the second equation by 2 or -2.
Yeah, and then like add them or something.
And then add them together. You get like -y is -7.
A lot of ways to solve system of equations.
Or you could take linear algebra.
And you could do some other things. Exactly. I'm going to go ahead and put this down here.
somewhat erroneously named.
I don't want to lose this information in the notes, but you're right. I do not like the fact that linear algebra is named linear algebra, but whatever. That's for another day.
Okay.
Is that what you're saying?
Alright.
That you said it's erroneously named?
No, I think Gaussian elimination. It's named after Gauss,
Oh.
but like Chinese did it first.
Yeah, true. I mean, yeah. I thought you meant
It's
linear
actually
algebra.
a very interesting series of journal entries, just like a really deep dive into Chinese mathematics. It's just like, wow, it's pretty cool. So if you're looking for inspiration ideas,
Boom.
anyway,
Anyways, all right. So we are going to solve system of equations with in polar, and we're going to see if those strategies that we just talked about work. Let's find out. What do you want to do first? We have a bunch of different ways we can solve this system of polar equations.
should we make like a table and write stuff down, or should we just go for it?
I think. Well. So, what do you mean a table and write stuff down?
Like, should we like point plot in polar?
Yeah. Well, let's point plot it, but we kind of know what these curves look like, right?
Mhm, yeah.
Yeah. So mine's like a. Let's see. I have cosine 2 theta, so it's going to be a rose with 4 petals. It's going to be it's going to start on the polar axis at 3. It's like my starting point is right here. You want to put your starting point down?
Did you want to put yours in the color? That okay.
Yeah, I do. I was already on it. Don't worry.
Right.
All right. So this is like my starting point. I'm going to write start there as well.
Okay. And then I'm going to start the opposite of where you are, actually, because I have -3.
Yeah.
My drawing.
We have the ray in the direction of 0, and you're plotting in the opposite direction. I was talking about that with someone today in class. Negative radial length goes in the opposite direction. Sweet. Awesome. All right. So we're kind of starting at different spots. All right. Let's proceed. Let's both do pi over 6.
Okay.
You have so much easier than me.
And then I go the opposite to where that is. Okay.
So I'm gonna put theta equals 0 at my starting point, and I'm gonna put theta equals pi over 6 at my next point. My next point is gonna be at pi over 6. It's gonna be cosine of pi over 3 because I'm multiplying by 2. Cosine of pi over 3 is 1/2 times 3. That's 1.5. 1.5 right there. Theta equals pi over 6. And I'm kind of like descending towards the gravity well of this pole.
Cool. I
Cool.
am going counterclockwise.
Right. At pi over 4, we don't need to do pi over 6 and pi over 3 from here on out. Let's just do increments of pi over 4.
Okay.
I think pi over 4 is where I am at a pole. Because pi over 4 times 2 is pi over 2. Cosine of pi over 2 is 0 times 3 is 0. So at pi over 4, I'm going to be approaching the pole. I'm going to be tangent to pi over 4 at pi over 4. Sweet.
And then I guess I can connect.
Yeah. Cool. All right, let's proceed. Let's go at 3 pi over 2. No, sorry, not 3 pi over 2. I'm looking at kind of where we're going together. Let's do pi over 2. Cosine of pi over 2 times 2, that is pi. Cosine of pi is -1. 3 times -1 is -3. Ooh, look at that.
It's the same.
Boom. Let me descend towards it. Notice I said descend. What is my R value?
Your R value is negative.
Yeah, it's -3. And what is your R value?
-6.
Yours is always -3. I'm quite jealous. I should have given myself that one and given you this one.
No,
We-
you're being generous.
We have the same theta value and the same R value. My R value is -3. My theta value is pi over 2. Your R value is -3. Your theta value is pi over 2. We have found a solution. And the graphs are intersecting there. All right, let's keep going. All right, let's do 3 pi over 4.
Wait, hang on. Can we like signify that we had an intersection there? Like,
Bam! You had that in the pocket waiting. I'm so happy.
I just didn't do it the right size. Okay.
Now copy that one so that it's the same size every time. Bam!
True.
Love it. Okay. Gotta let that one like marinate. Okay. Let's plug in 3 pi over 4. So I'm multiplying that by 2. 6 pi over 4, 3 pi over 2, cosine of 3 pi over 2 is 0. Oh, I'm going to be back at the pole.
Then I'm out here,
Sweet.
just living my life.
Just living your life. All right, now let's do pi. So that's 2 pi, cosine of 2 pi is 1, 3. So pi, I'm going to be at 3. Oh, I'm intersecting your curve.
But that's not at the same theta that I was at.
Right, yeah, so we need a coordinate pair that satisfies both equations.
Mhm.
And my coordinate pair here is theta equals pi, r equals 3. And yours is theta equals 0, r equals -3. How about where you just hit my graph?
Well, that's also like we're kind of just missing each other. It's like you were on a train and I was on a train and they weren't in the same places at the same times.
What are we looking for
And
in your train
yeah.
analogy?
a train crash, I guess, which is maybe less desirable.
I
Okay.
know. This is a good. I think this is a good moment to bring up the various analogies that the teachers at Blair hold dear. So I'm a big fan of Mr. Schaefer's analogy for polar intersections, and the way he thinks about it is he's an evil scientist, and he has mice. He does experiment on animals, and he dips the mice into paint, and he puts them onto a very large polar graph on the ground. And then he has brainwashed them to run in polar curves. And we are looking at not when the paint trail overlaps, but when the mice run into each other. That is what we're looking for here.
Mhm.
Then there's Mr. Stein's analogy, which is similar to the one you just used, which is cars and intersections. And let's just keep drawing these curves. All right.
Okay.
Let's see if there's any more BAM moments. All right. 5 pi over 4. I'm going to be at 0 again. At this point, I'm kind of got an idea of what my curve is doing.
All right. And I'm going to be up at pi over 4.
Sweet.
Like
No intersection happening yet.
Or maybe it's like superheroes, like superhero flight patterns.
I've never, one day after, we all have to leave our planet and go to a new planet because we killed our planet. And we go to a new planet system and their sun happens to give all of us powers. You know what I'm saying? There's going to be 6 million people flying around. Imagine if all of Krypton came to Earth. It'd be 6 million people flying around, 6 billion people flying around. There would be flight patterns and traffic jams in the sky. I don't know where I'm going with this. Let's keep going.
Yeah.
All right. 3 pi over 2. I'm going to be at -3. I'm going to be right here. I think this is about to be another intersection.
Boom.
Bam.
Yeah.
Bam. Chapow.
Oh, it didn't copy the right size.
And no, I think you need to take a screenshot of the. Kami is not perfect, but who among us is? Let's keep going. We have an intersection there, so we have another solution. So wait, our solutions are so far we had theta equals pi over 2. Do you see why I wish that theta went first?
Yeah.
You kind of see it, and then we just got 3 pi over 2.
But sometimes, you just have to live with things.
Yeah. I'm sure there's a legitimate reason that I don't know about. Anyways, let's keep going. And I think we're not going to get any more intersections. I come down to the pole at 7 pi over 4.
I'm over here.
And then I'm going to finish my cycle at 2 pi back where I started. And I believe you will as well. Not too shabby. Our curves are pretty nice.
I would say that mine is a little bit easier.
Yeah, but I mean, drawing a circle well It's tough.
Mm.
In in-person school, I usually have a circle drawing contest every year around the triangle times.
Well, we could have a common circle drawing contest. And everyone's a winner, and you all get participation trophies.
That's a line. I tried to draw a circle and it was a line. Look
And
at my.
Mr. Kirk. And
All right. There we go. There we have it. That is those are our that is between 0 and 2 pi.
Mhm.
Those are our system of equation solutions.
Sweet.
Obviously, there's more if we were to continue, but the question we didn't explicitly say this, but I underlined it a while ago, 0 and 2 pi. We were looking for solutions.
Hmm.
Right. The answers better be -3 because your R is always -3.
Mhm.
So for any 3 blue 1 brown fans out there, I actually had a student last year who was getting into Grant Sanderson released his I guess I don't know his code, or he did some instructional videos on how to make his animations. And I had a student, shout out to Michael, make this problem in the fancy 3 blue 1 brown programming. Let's take a second to watch it. Here it comes, here it comes, here it comes. Bam! No bam. No bam.
Get ready, get ready.
Bam! No bam. Oh, so nice. So
That's
nice.
nicer than the one that we did by hand.
I know, and that one's in real time too. It's really nice. Thank you very much to Michael from last year. Thank you very much. There you have it. How else might we solve this system of equations?
Well, it says solve the system algebraically / trigonometrically.
Mhm.
So maybe we should do that. It's like
Okay.
set those equations equal to each other and then kind
Yeah.
of like just do some stuff.
It's like 3 cosine 2 theta
Mhm.
is equal to -3.
Yeah.
I feel like this is just a problem that we did back in the day.
Mm.
Who's old enough to remember doing this problem back in the day? Divide by 3.
Am I supposed to raise my hand? I don't know. -1.
When is cosine -1?
At pi over when is cosine -1?
It's just pi, right?
At pi.
Pi plus 2 pi k. Only one time per period. It's one of the 2 special angles that. And then, so I actually don't need this bracket.
Then you divide by 2.
You divide by 2, and we get that solution. All right, so solving algebraically is clearly more efficient. But the whole point of this lesson is to recognize that if looking at polar curves, the intersection of polar curves may be deceptive. If I just threw those graphs on the page, you might not realize that those were solutions. If we said this, if R equals 3 was your graph, we would have gotten, I think we would have gotten 0 in pi, but no 3 pi over 2 and pi over 2.
Mhm.
So don't let a graph deceive you. We're looking at for when the trains collide, not when the trains calmly pass each other. Let's proceed.
I think the superhero fight.
Okay, I'll start using that one.
Yeah.
Okay.
Because then, like, you know, it's like yeah, they fight, but then like they can continue going on their like merry way.
Wait, can my trains just be full of bubbles?
But like if trains collide, that they're still gonna be broken because it's
Yeah.
a train.
Yeah. Yeah.
Whatever.
All right. 2 plus 3 cosine theta and 6 cosine theta. I'll let you pick this time. Which one do you want?
I'll take the first one.
Okay. Same colors?
Sure.
How many legs does a crab have?
I think it has 6 and then 2 claws. But yeah, 6 legs, 2 claws.
Mine just looks like a spider with a mustache, but okay.
Are those your claws? They're very dangerous.
Yeah, they are.
I see. It's fine, Mr. Kirk. You can draw crabs wherever you want to.
Still not that great, but anyways. 2 plus 3 cosine theta, 6 cosine theta. So let's look at when these two things intersect. Let's go ahead and graph these things. 6 cosine theta. I'm starting way out here at 6. Ooh, I have a circle that is going to make its rotation twice in the span of 2 pi.
Okay. And so I have 2 plus 3 cosine theta, so I'm going to start at 5. Which
Circle.
I'm just going based on your thing is just 1 in from there. So I don't want to count to 5. So those are not intersection.
Yeah, no intersection there. I think we're about to intersect though in a second, because I believe we're both about to get sucked into the void.
Are we labeling?
I'm very dark today. I'm very sorry about this. I'll try to tone down my my darkness. Yeah, I went ahead and wrote circle radius 3 x-axis symmetry.
Okay, and then I think I'm gonna have a limaçon. Is it gonna be a looped one or a dimpled one?
I think it's going to be looped because we will be getting to negative numbers, right? 2 minus 3 is going to be a negative number.
True.
Okay, so a loop-de-loop.
Looped limaçon. Okay.
All right, so let's see.
What should we plug in next?
Let's plug in pi over 6.
Okay.
At least for these first few, let's plug in pi over 6, pi over 4, and pi over 3.
Okay. So
because I have a feeling we're going to intersect at one of them. I don't know which one though. Cosine pi over 6 is root 3 over 2 times 3 is 3 root 3 over 2 plus 2. I got a calculator here. 3 root 3 divided by 2 plus 2, 4.59.
Can you do my math for me too?
I can.
2 plus 3 times root 3 over 2.
Wait, no, that's the one. Oh, no, I just did yours. I'm sorry.
What did you say?
I did yours.
You did.
So your
Okay.
point's right there. Sorry. So go ahead. Mine is just
Beautiful.
6 times root 3 over 2. 5.19. All right, so I haven't gotten to you yet. Descending. All right, let's do pi over 4.
Okay.
Root 2 over 2 times, I'm going to do yours, 3 root 2 divided by 2 plus 2. 4.12 minus 6 divided by 2, 3 root 2 minus 4.24. Oh, we're getting close. I have a feeling an intersection is about to happen.
That is, yeah. Very good.
These superheroes are about to bam,
I need to go.
collide. All right, let's do pi over 3. So, oh, this is an easy one. We can do this without our calculator. Mine's going to be 3.
And then, so I have 2 plus 3 times 1/2.
Oh, yeah, 1/2. So 3 halves. So 2 plus 3 halves, 3.5. Oh, look at that. It wasn't a beautiful number. It's not a nice rational number. We are intersecting between pi over 4 and pi over 3.
However, we still get the
I knew that was coming.
too big.
I'm more excited than I think anybody is. Okay, so we intersected. We don't know where that is. I think the only way to do that, we do know that that point is an intersection.
Mm-hmm.
We were there.
You know, like what it's between.
Yeah. If you want to know exactly what it is, I think algebra is the move.
Okay.
But we do know it's a solution. That's kind of what the graphs tell you. And watching them chase themselves out is it even a solution? And we hit that spot at the same time. My next point is going to be at 0. What's your next one going to be?
And then
I think yours is going to be 2. Cosine of pi over 2 is 0. 0 times 3 is 0 plus 2. Yeah. I'm going to use my symmetry, but I can help you get your next number.
Yes, please.
What should we do next for you?
is 2 pi over 3. Does that make sense?
Yeah, well, let's do 2 pi over 3. So that's going to be negative 1/2. So 2 minus 3 halves, it's 0.5.
Here. Oh my gosh. I really want to zoom in more.
Meanwhile, I'm way over here in the fourth quadrant.
Wow. Nice knowing you.
Yeah. Oh, you're about to pass through. Let's not worry about figuring out when you pass through. Let's just see
Okay.
what you are on the other side. So if we
Right.
plug in 2 minus 3 root 2 over 2, 2 minus 3 root 2 over 2, negative 0.12.
It's like,
So you've like just before 3 pi over 4, you're passing through inconveniently. I can give you 5 pi over 6. That might be
Okay.
that might just be a little
that
bit
might
easier.
help. Yeah.
Yeah.
Less than
So
four.
it's gonna be 2 minus 3 root 3 over 2. That's a quick calculator move. Negative 0.6.
Okay. So somewhere like over here.
This is a good chance to talk about that overlapping point. Is that a solution there at the pole?
Mm-mm.
No. I got there way at pi over 2, and it took you until somewhere between 2 pi over 3 and 3 pi over 4 to get there. Yeah, so that is not a solution, even though we're overlapping. I got some more symmetry I can do. Boom.
I have pi over 2. If I have pi, then I have negative 3 plus 2, so negative 1.
Oh, nice. It was a nice one.
Yes.
And then now you have some symmetry, right?
I do indeed.
Yeah, so go ahead and grab that
Kind
symmetry.
of derpy looking, but that's okay.
Wait, time out. Where are you at right now? Are you at pi?
I'm at pi.
Yeah, and I'm at pi too. So I'm way over here at pi.
Oh.
And you're right there at pi. Let me go ahead and write my
That's like almost as far away as we've ever been.
I miss you.
It's okay.
So I'm going to trace out my circle again,
Mhm.
and you are going to just finish out your limason, I think. I don't think we're going to intersect. As you graph more points, I'm going to like think about where I am. Okay, so you're back at the pole again, and I am. When are you at the pole?
I am at the pole somewhere between.
We might be intersecting here
Oh,
because
maybe.
I'm back at the pole at 3 pi over 2.
Mhm. But this is somewhere between.
Oh wait, you're right. It's not. Mm-hmm. Yeah.
Over 6 in this over.
Yeah, because at pi over 2, you're going to be
Down here.
yeah at 2 at 2. Yeah, never mind. Not an intersection. That's disappointing.
It's okay.
I thought we were gonna meet again. We will meet someday. All right, and then okay, so now you're at 3 pi over 2. I'm at 3 pi over 2. I think we're about to meet.
Mm-hmm.
Right, because I'm coming, and I'm right there, and then
I think I'm somewhere over here. Right, and then because I need to pass through.
yeah, and as you get closer to there, I'm getting closer to there, and I believe it's going to be a bam moment.
Yeah.
Hey, what's the name of the Flintstone?
Bam bam.
Shit? Bam Bam. I feel like there's some comedy gold for our taking. I don't know. Next time. All right, and I believe we're going to finish this out, and we will not meet until a new cycle.
Mm-hmm.
All right,
So
let's
it's
figure out
only
what
every,
those two solutions are.
Yeah.
2 plus 3 cosine theta, 6 cosine theta. Excuse me.
So should we combine our cosines? So
Yeah.
2 equals 3 cosine theta. Oh yeah, 2/3 equals cosine. I mean, it has to happen. It's just
Yeah,
when.
calculus says so. Let's find arc cosine. Let's see if I'm in radian mode because I've been in degree mode a lot lately. I am back in radian mode. Arc cosine of 2 divided by 3 is 0.841. What is my other solution? Do you remember the trick?
Is it a plus 2k pi?
So we're dealing with cosine here. Where on the unit circle? So where on the unit circle has a x coordinate of 2/3. I just got 0.8. Where else on the unit circle? It's an
Down.
x down, yeah. Negative 0.841 plus 2 pi k. So, but we want them between 0 and 2 pi. So let's actually add 2 pi to that second one. Times -1 plus 2 pi. 0.841 and theta equals 5.442 radians. Have we finished?
No, because we still need the r's.
You're right, yeah. So we have 2 coordinates. The theta goes here. But we need those r values. And I believe, what do we need to do? Just plug it in, right?
Yeah,
Yeah,
and
6.
we got that from what? Arc cosine of 2/3. So
Ooh.
do cosine of arc cosine, that goes away, right? So we
Yeah.
have 6 times 2/3.
Cosine of the arc cosine of 2/3 is equal to, oh, but it's 6 cosine. 6. We need to be careful about when we cross our cosines and our arc cosines out because they're not truly, I think these will always cancel. Yeah, we can cross those out. 12/3.
Also known as 4.
Also known as 4. 4. Boom. All right, let's see.
4 there?
Oh, we totally did not graph these beautifully.
Yeah.
We did not. Let's great segue to Michael's. Let's see if it's loaded. It has. Awesome.
Nice.
Sweet, sweet, sweet. Let's watch it being done by a professional.
Unless it doesn't load.
I don't know. Let me just pull up the raw file. Really hoping I wouldn't have to do that, but
I was wondering about the etymology of refrigerator. So, okay. Nice.
Wait,
That is at 4.
We need to go back to what you just said, but you're right. Yeah, it is a 4. And then we did not intersect at the pole, even though it looks like we may have.
Mm-hmm.
And then wait for it.
Bam. Bam. Nice. Exactly a 4. Beautiful.
That's nice. That's really nice. Who would have known? Who would have known that a perfect computer generated graph would reveal that the answer was such a great whole number?
Mm.
There it is. Control tab. Control tab. We're back. All right, there we have it though. We have our intersections. We have our intersections up here. We this one is in the bag.
Nice.
Oh, we forgot to title it.
Oops. Quick before we turn it in.
Oh, I don't miss those days. When students would turn things in without their name on it. Now the computer just does it for them.
Mm-hmm.
All right. Wait, so let's close this one out by revisiting what you just said. Did you do any research on the etymology of the refrigerator?
No, because it's like it's more fun to kind of speculate and like think about it for a while, and then if it like is worth bringing up again, like instead of immediately looking it up, it's like fun to like just do the thought experiment. So I had gotten to the thought experiment part, and then hadn't gotten past that. Because also like while you're driving, you know, you like don't want to like look at your phone, like look stuff up, it's not safe, and then you know my husband was in the car, so like he was navigating with like a phone, so I didn't want to. Yeah.
Wait, can we take a second though?
Wants to. Yeah.
Refrigerator. So something's
why is
being
there a re?
redone. Yes. It's being refridged.
Hmm.
Huh. So what does fridge mean? To fridge. Is there a refrigerator? Is that like the opposite of making something cold?
Maybe, but
But
also like part of the wondering was also what's the difference between like a refrigerator and a freezer? Like because the freezer is going to make it to like a freezing temperature, but where do you draw the line? Like, are you using water as your basis for that? Or
it might not be water. It might be, I don't know. I think it must be water. I don't know. But also, growing up, called the refrigerator a fridge.
Mm.
And if the is important in the etymology of this word, then calling it a fridge might be contradictory.
Mhm.
This might be a big existential crisis that I am about to embark on.
Mhm.
Hey, if you figured it out, let me
Have
know.
fun with that. Or it can be a interesting as long as you can connect to math somehow. Math's turn on top of it, yeah.
Yeah, if someone could talk about, talk about temperature,
Mm.
maybe talk about the conversion between Celsius and Fahrenheit in there, and Newton's law of cooling and stuff like that.
Newton's
That's
law of
all.
cooling. There you go.
That's all mathy.
Mhm.
But also we're curious. So if you want to figure it out, let us know. Synthesize that information for us. I think we'll leave it there. Ready to close this one out?
Yep.